Hey guys, Professor Doney back. We're in the middle of talking about conservation of energy. Good concept to solve a lot of different types of problems, and I think a little more easy depending on what problem you're looking at. Certainly can simplify things. So over here on the right we have our conservation of energy equation. It says the energy total at one point equals the energy at two. That comes out of, or we can rewrite that as, see if I can find my cursor here, the change in energy equals zero. That means nothing is lost. We don't get anything. The difference between these two is zero because they equal each other. And we expanded that equation to say that the potential due to spring, potential due to gravity, potential due, or the energy due to kinetic, has to equal potential due to spring, gravity, and kinetic at the second location. So let's do a little different problem here. We're going to have our little car or roller coaster, and let's say it's going at 10 meters per second at the top of this hill, and then it's going to roll down the hill and it's going to come out here, and there's our car, and we would expect it's going to be going a little faster when it gets to the bottom of the hill. Let's put some dimensions on here, pick out some other colors, and just for some easy numbers, let's make that 10 meters up. And we're going to call that point B, and we'll call that point A, and let's give mass of the car of 100 kilograms. Alright, 100 kilograms. Just again for easy numbers. It's not much of a car, it's probably more of a go-kart kind of thing, but again, easy numbers. So, using energy. Now, it's not quite a drop problem because things are moving horizontally and vertically at the same time, so we can't use those equations. So we're going to look at this as far as energy. And what we do is we come back to our energy equation here, which is expanded out. And I like to look at the entire equation right off the bat and then just look at what we have at each location. So, at point A, let's look at what we have going on at point A. At the top of the hill, do we have spring energy? No. Why not? Well, no spring. Alright, do we have potential due to gravity? Absolutely, because it is above the ground. It is at a certain height. It's not at h equals 0, which would be the end of the problem here. Is there kinetic? Well, if we see the car initially is already moving before it goes down the hill, so yes, it has energy. Now this is also, we're going to see, they want to go faster by going down the hill. It's sort of like the bobsled. They don't just start at the top, get in the sled, and let it roll down by gravity. They actually give it a little push, a couple pushes, or rock it back and forth, give it a final push to give us some extra energy to start the problem. That's what that is right there. Alright, get down the hill. We don't care, again, energy doesn't care if it does this, or it does this, or it does this kind of path. It just goes from A to B. B, what do we have happening? Do we have a spring? No, no spring energy. Is there potential due to gravity? Well, no, because our height, we're at the bottom. We're saying we're at the bottom of the bottom. Does it have kinetic? Oh, absolutely. So what happens, all this potential gravity plus the little kinetic it has from initial velocity goes into kinetic energy at the bottom, making it go fast. So when we write that equation out, it's going to look like this. Potential gravity up at A plus kinetic at A equals all the kinetic happening at point B. Okay, and there's really your whole equation. Now we just have to put it together and pull out the this, so it's going to be mgh at A plus half mv squared at A has to equal half mv squared at B. And just real quick here to get through the math, we can get rid of the m's because everybody has an m, and we find out that the velocity of b squared is going to equal on this side, let's see, 9.8 times the height, which is 10, plus half of the initial velocity squared, which is 10 squared, and vb will be the square root of whatever that number is, which is 98 plus 50, so it's a square root of 148, which is 12, a little over 12 something meters per second, VB. What we need to check here is to make sure that at this velocity is greater than where we started. It is, so we think that's a good problem. And I'm out of time. How quickly 5 minutes goes. Alright, see you next video.